All right, so let's kind of pick up then where we left off. Hopefully those 2 videos that I posted help you kind of understand this idea of precession. So are there questions about either the precession thing or about conservation of angular momentum? Okay, cool. So the only other thing we need to cover, this was one of those random equations that if this showed up on the AP test, I would be pretty surprised because it's a real specific question. So anyway, have I covered everything here? Let's see. A non-spinning gyroscope falls, it's the torque. Here's the spinning gyroscope, the torque causes it to change its angular momentum. It's called precession. Cool, we talked about all that. All right, cool. So one of the things that we might be interested in is when you spin the wheel, at what rate does the wheel precess? Okay, that's what that's called. You know, the wheel is spinning around this way. It's called precession. So one of the things we might want to know is how quickly does it do that? Okay. And so I'm not going to go through the derivation, all of this. It's basically some similar triangles. But it turns out that this formula here gives you the equation for the angular velocity at which the wheel precesses. Okay, so there's 2 angular velocities here. Omega represents the angular velocity of the wheel itself. Okay, this represents the angular velocity at which the wheel kind of spins around. Follow? All right, and it's largely just plug and chug. This would be the mass of the wheel, G obviously a G. R here is the distance from, where's the wheel? Thank you. R would be the distance from the rope to the center of gravity. Okay. This term here is basically just the torque produced by gravity. Follow? Okay. And then divide that by I omega, where I is the rotational inertia of the wheel, and omega is the rate at which the wheel is spinning. Good? Yes?
How fast it spins like
This way, correct. Make sense?
Yeah. Wait, so W and WP will have
This just gives you the magnitude.
Oh.
And then to find the sign, you got to do the whole right-hand rule thing and think about which way the wheel's spinning. And there's not really an easier way to do it. All right. Okay. And then a quick comment. I like this notation better, using omega p as in angular velocity of the precession. The book uses the Greek letter omega though. Okay. It's the same equation, but they use the capital letter omega instead of omega p. Capital omega. Good? Okay, cool. And I think there's one problem in the homework where you use this equation, and it's literally just you're given all these values and you plug them in, and it works. Cool? All right. My original intent was to actually try to figure it out with the tire, but I think trying to calculate the angular velocity of the tire would be, I think we could do it, but I don't know that I want to take the time to do it since we're already running behind a little bit. Okay, so. All right, so questions on all that? We good? Okay, so that's pretty much it for chapter 11. Please make sure you spend a minute with that precession problem at the end of the last homework assignment. If you guys have questions on it, obviously let me know, and we'll go over it. But I think it'll be pretty straightforward. It's just, like I say, it's just that one equation. So tomorrow I'm not here, so I'll leave stuff out for you so you guys can play with the wheels and the spinning and the stuff. And then you guys should use the time to finish up worksheet, what is it, 11, 4, and 5. Okay, because that's due on Thursday, and then the last stuff, this stuff is due on Friday. Cool? Questions? Okie dokie. So, let's talk about equilibrium. Did everybody grab the note packet when they came in? Go grab that. Oh shoot, I forgot to... Oh. All right, so chapter 12 is really just one kind of problem. And I like these problems. I think they're neat. They're nice because they're all solved using the same two equations. Okay. So anyway, getting ahead of myself a little bit. All right. So what we're going to learn about is what's called equilibrium. All right. Before we do that, we got to learn a couple of just kind of basic things. None of them, I don't think, mind blowing. So I don't know what was it? Chapter 9, maybe we learned about center of mass, right? Okay. And at that time, what I told you guys was that when you were calculating the torque, no, we hadn't done that yet. Why did we use center of mass? Oh, because we were doing momentum. So when you're talking about conservation of momentum, the center of mass became important. So this chapter, we're going to be interested in not just the center of mass, but also the center of gravity. Okay? So in the same way that the center of mass is the average location of an object's mass, center of gravity is the average position of an object's weight, right? Because force of gravity is weight. Okay? Now, for most objects, they're the same or so close together that we treat them as being exactly the same. Okay? But technically speaking, they're not exactly the same. All right? So here's a real simple example of a thing where the center of mass and the center of gravity would not be the same. All right? So imagine the Earth with a very, very tall tower. And just for simplicity, let's assume it's like just a solid obelisk, like that thing in 2001. So it's this giant stone obelisk that's whatever, miles tall. Okay? So, assuming that it's uniform, then your center of mass would be at the geometric center, right? Good? Now, we haven't done gravity yet. That's actually chapter 13, but I think you guys, when I mentioned gravity before, you guys were like, oh yeah, we know that. So one of the things you hopefully know is that as you get farther away from the Earth, there's less gravitational pull, right? So if this thing is substantially tall, what that's going to mean is the top half of it, because it's farther away from the center of the Earth, is going to weigh a little bit less than the bottom half, right? Okay? So if we think, instead of thinking about mass, if we think about weight, because the bottom half is the heavier half, there's going to be more weight lower down. And so our center of gravity is slightly below the center of mass, simply because the bottom half weighs more, because it's closer to the Earth, and therefore gravity is pulling on it with more force. Follow? Yep, Alex?
Wait, so does that mean if you like took a basket to go to the top of Mount Everest and walked on it, you'd weigh like a little bit less?
Yeah, and when we do gravity, we'll do those calculations. And yeah, it's exactly right. It's exactly right. All right. So, does this make sense, you guys? Right. Now, there's one problem in your book that's about this. So here's the basic idea, you guys. You guys remember, how do you find the position of the center of mass? You guys remember how to do that? Yeah, so what you had to do is you had to, for each particle, you had to take the mass of the particle and multiply it by the position of the particle, and you had to add that up for all of the particles, right? And then you divide it by the total mass, right? I think sometimes we just wrote a big capital M, right? So this is to find the center of mass. How do you think you find the center of gravity? Yeah, you replace M with, well, you got to be careful though, because G is a constant. You have the spirit of what you're saying is right. G is a constant. That's always 9.8. But if you go to the top of Mount Everest, G is now 9.79 or whatever. It's not even that much less, but it's a little bit less. So, to find the position of your center of gravity, instead of looking at the masses of the particles, you look at the weight of the particles. So you would take the sum of the force of gravity on particle I and multiply by the position of particle I and divide that by the total of all the weights of all of the particles. Cool? So the calculation is the exact same thing, except for each particle, you got to multiply the mass by whatever the acceleration of gravity is wherever you're at. Okay? Which basically amounts to the strength of the gravitational field, but yeah. All right, cool. So I think there's one problem in the book about it. If you just kind of follow your nose, it'll work. I'm sorry?
It's an oddly specific question.
Yeah, totally. So, all right, good? All right, cool. So that's center of gravity. So why do we pick? So when I take, I'll use this because it worked last hour. So if I take this giant ladder, oops. Theoretically, I ought to be able to balance it. I'm not going to try to because it's just on a point. But clearly, if I lean it like this, oops, and it doesn't open like that, if I lean it like this and let it go, it's going to fall, right? Okay? Because my pivot point is down here at the floor, and my force of gravity is pulling it down. But to calculate the torque, I need to know where to treat that force of gravity, right? So where do you think I do it? At the center of gravity. Okay? So what I can do is I can kind of treat this whole thing as being sort of a massless thing, or I guess I should say a weightless thing, with one force equal to the force of gravity acting at wherever its center of mass is. Okay? And so then what that does is it produces a torque and causes this to rotate all over. Cool? Right? Oh, in fact, we talked about that when we did the problem about the guy lifting up the plywood plank, didn't we? Right? So, all right. So anyway, so that's why we care. So the reason the center of gravity is important is because when you're looking at torques on an object, if gravity produces a torque, you treat that torque as acting at the center of gravity. All right? So this is all a review. I think you've had this exact same screen before. Net force causes acceleration, net torque causes angular acceleration. This is all review. Here's our equation for torque. Remember, it's, what's D again, you guys? Yeah, the lever arm, the distance from whatever your pivot point is to where the force is. Remember, theta is the angle between the force and that D, the lever arm. Okay? So yeah, I think I just copied and pasted some of this. Do you guys need me to go through another one of these examples where the force is at a weird angle? I should have just deleted those 2 pages. Okay, so let's do an example here. And I changed these, and then I apparently didn't save my changes. So the copy I printed for you doesn't have these changes. So there's a couple things up here in red that I changed. So fix them on your notes. So I think on your sheet it says that the teeter-totter is massless, right? Yeah. All right. So here it says, suppose a teeter-totter has a uniform 20-kilogram board, which is 4 meters long. The fulcrum is oops, there's another typo. The fulcrum is 1.5 meters from the end. Sally, who has a mass of 60 kilograms, sits at the short end of the board. So the question is, where does Roy have to sit to balance the board? Okay. So with these problems, a good drawing is 100% your best friend. Okay. So please make sure you make detailed drawings. All right, so we've got this uniform board that's 4 meters long. So let's draw that. So here's our board. It's 4 meters long. 4 meters. And then it tells you that the fulcrum is 1.5 meters from one of the ends. So all right, now, in a minute, Sally and Roy are going to sit on this thing and hopefully get it to balance. Before we do, if nobody was sitting on it, what would this board do? It would tip over, right? It would go this way, right? It would, the way I've drawn it, it would rotate, what, counterclockwise, right? All right, I was have to stop and think about clockwise, counterclockwise. All right, so the reasoning behind this is this. So here's my beam, here's my fulcrum. All right, so you can explain that 2 ways. One way to say it would just be to say, well, there's more weight over there, so it's going to fall that way, right? Okay. Another way to say it would be to say, well, if you find the torque produced by this side, well, this side has a center of gravity that's like right here, right? Okay, so I could calculate the torque produced by the weight on this side. So I'd have a little force, because there's not that much weight, times a little distance, right? And then do the same thing on the other side. I've got more weight, so here's my center of gravity of the other side, times a bigger force. And the torque on this side is going to win, right? Right? But the easiest, most efficient way to do it is this. Calculate the center of gravity. The center of gravity acts here at the 50 centimeter mark, right? So what happens if I push right here? It rotates that way, right? So that's why it tips over. Because we can treat this whole beam as being massless, weightless, I should say, and just a force of gravity acting at its center of gravity. Follow? Okay, so right now, we've already got one force that we can put on this thing. So right here, 0.5 meters from the fulcrum is the force from the board itself. And the problem tells us it's a 20 kilogram board, so 20 times 9.8 is 196 newtons. So that is, already there's one force on the board. Does that make sense? Okay, so next fact. Let's see. Sally, who has a mass of 60 kilograms, sits at the short end of the board. So here's Sally. Oh. All right, and she's got a mass of 60 kilograms. So that means that her weight, so the force of Sally, is going to be 60 times 9.8, which ends up giving you 588 newtons. Good. And then there's one other force. We got to put Roy out here somewhere. So here's Roy. He's going, where do I sit? He's going to exert a force of 100 times 9.8, so 980 newtons. You could probably pretty safely hazard a guess about which side he's going to sit on, right? It won't always be obvious, but in this one I hope it's fairly obvious, right? So right now, between these two torques, which one's going to win, the blue or the red? The blue, right? You got more force and more distance, so totally that's going to win, right?
Yeah.
So right now it would rotate this way, so clockwise, right?
Yeah.
So we need more counterclockwise force to make it balance. Follow?
Yeah.
All right, so to make this thing be in equilibrium, we want it to not move up or down, and we want it to not rotate clockwise or counterclockwise. All right? So to solve this thing, there are two equations we're going to use. We're going to have one equation which tells us that the net force is 0, and one equation which tells us that the net torque is 0. Follow? All right, so first thing we got to do is identify our forces. So I'm going to arbitrarily put the force for Roy over here somewhere, and then we'll figure out where it goes eventually. But let's at least put it in the drawing. I know that Roy is going to be sitting, hopefully at this end, if my thinking was right. 980 newtons. Are there any other forces? Normal force, right? Where is the normal force acting? At the fulcrum, right? So there's also a force from the fulcrum, right? So you don't think it's friction. Cool. So I can certainly find that the force of the fulcrum by using one of those two equations I just told you, right? So let me clear up a little space on the board. From there. My way. Oh, I guess we'll shrink the problem too. Okay, so here we go. Net force is 0, right? Because it's in equilibrium. We don't want it to move at all, right? So what that means is, well, let's see, net force is, and I'm going to do this in way more detail than you'd have to, because this problem is fairly basic, and I want to sort of model how you would solve a harder problem. Okay? So I'm going to write it all out. So my net force would be the force of Roy, plus the force from the board, plus the force of Sally, plus the force from the fulcrum. And solve for your missing force. So my net force is 0. Force of Roy is 980 down. Force of the board is 196 down. Force of Sally is 588 down, plus the force of the fulcrum, and solve it. Notice I kept track of my signs, right? Anything that was down, I made a negative force. Anything that was up, I made a positive. I gave myself a paper cut during tutorial, and then 3 minutes later I picked up a piece of paper and gave myself a paper cut across the original paper cut. Yeah, it hurts. Okay, so anyway, if you solve this, the force of the fulcrum turns out to be a number that I've written on a piece of paper that's laying somewhere in this room. Is it 1519? Anybody figure it out? 1364, that doesn't ring a bell. Oh, you know what I did? I solved it with my wrong answer. What does it give you then? 16 what? 1756.
Yeah.
Do I agree with that?
Great.
It can't be 56 because those don't have. I got 64. 1764. All right, thank you. I apologize for not having. All right, so is everybody good with that? Okay, so cool. Let's put that in our drawing. 1764 newtons. All right, cool. So now the other thing I need to know is where Roy is going to go, right? Okay. So the idea is, if he sits too far one way, then the board will rotate this way. If he sits too far the other way, it'll rotate that way. We don't want it to rotate. So we want our net torque to be 0. Follow? So when we do that, can I erase the black? Has everybody got that? Okay. So when I do that, when I say my net torque is 0, intrinsic in that statement, when you talk about net torque, you have to identify a pivot point. It doesn't make sense to talk about torque if you don't have a pivot point. So where would my pivot point be in this problem? Where the fulcrum is, right? Because obviously if it tips over, it's going to tip around this point. All right, so I'm going to use, I guess, a big green dot and label this with a P for pivot point. Cool? And now what I'm going to do is I'm going to write an equation that allows us to calculate the net torque around P, around that pivot point. And that's the notation I'm going to use. I'm going to write a little letter next to the net torque symbol to indicate where the torque is being found around. Follow? So the net torque around pivot point B should be, well, let's see, it should be the torque from Sally plus the torque from the fulcrum plus the torque from the board plus the torque from Roy. Follow? All right, so let's go through and find all of these. So let's see, the net torque has to be 0, right? Because we don't want it to rotate. Equals, let's see, torque from Sally. So torque is force times distance. Notice all of these angles here are 90 degrees, which makes things nice, right? So torque from Sally is going to be 588 newtons times, what would the D be? 1.5 meters. Is her torque going to be positive or negative? Clockwise, so negative, it points into the board, so put a little negative sign there. The negatives in this section get a little yucky sometimes, so be really careful with them. All right, plus the torque from the fulcrum. Let's see, torque from the fulcrum is going to be the force of the fulcrum, 1764 newtons times, what's my D?
0.
0. It's not going to provide a torque because my force is located at my pivot point. So neither positive nor negative. All right, plus the torque from the board, so that's 196, times what distance do I use? 0.5. All right, is that a positive or a negative torque? Let's see, right hand, radius, force, points out, positive. Or counterclockwise, positive. Okay, plus the force from Roy, that's, what does that say, 980? Times X. X. Good? So here's the deal with that. This is what I meant when I said that positives and negatives get a little dodgy here. You really got to just sort of use some logic here. So it turns out that, how do I want to say this? As long as your lever arm is perfectly horizontal, you can keep track of the signs on your forces and your D's, and it'll correctly tell you the sign on your torque. But as soon as you have a lever arm that's vertical, that messes everything up. So you really need to kind of just think creatively about it. So I'm going to leave everything positive here, okay? Notice I didn't make any of these forces negative, right? I'm not ignoring you. Let me just finish my train of thought. No, okay. Right? I made all of these forces positive, right? So this negative sign I had to sort of manually put in by realizing, oh, well, that's going to be a clockwise torque, right? So I manually put that in. So what I'm going to do is I'm going to assume that this is positive, and if it ends up not being positive, I'll get a negative distance. which just tells me that, oh, it shouldn't have been this way, it should have been that way. Follow?
Yeah.
So that's probably the safest way to do it. Okay, yeah.
So I usually think about those like so it equals 0 if it balances out. So I just bring the one to the other side and just solve this to two sides. So
And that very often works. How do I want to say this? There are sometimes problems where you don't know which side something goes on, which is why I like to write it this way. Okay? If you have another way that works and you're consistently doing it right, then badass. Totally. That's not me being snarky.
I want to check that way if that works.
All right, so follow? All right, so if you solve this mess, I don't need to go through the algebra for you, do I? Okay, so if you go through the algebra and solve this, you end up getting D equals 0.8 meters. It does turn out positive, telling me that that torque should have in fact been positive, which means that, oh, it's got to be this side. Follow?
Yeah.
All right, so awesome. And we already made our free body diagram. So there's our D. Is everybody good? Oh, except that I changed dx into D, didn't I? All right. Now, here's the wild thing about these equilibrium problems. Check it out. We just got this thing to rotate, right? So the net torque around this point was 0 because it wasn't rotating around this point at all, right? Follow? All right, I'm going to ask a really dumb question. How quickly is it rotating around this point? It's not. So what should the net torque around this point be? 0. If something is in static equilibrium, if it's not moving and not rotating, you can take any pivot point you want. All right, we've only got 2 minutes. Here's your one homework problem. I would like you, before I see you again on Thursday, to go through and use the net torque equation and calculate the net torque, not around the point that I chose as the pivot point, but calculate the net torque around point Q, let's call it point S, where Sally's sitting. Right? And see what you get. What should you get? 0. All right? And if you're blown away by it, pick any other point on the board. Any point at all, and calculate the net torque around it, and you'll always get 0. Yes?
But I just tried doing it like the center of gravity, where you just set your pivot point as your 0.
And so you put your pivot point to be here?
No, so I put it at the fulcrum. I set that to be 0 in the coordinate plane, and just said, okay, like the force of Roy has to be some x, and then.
So you made these negative distances? Is that what you're getting at?
Yeah, I got negative 0.8.
Okay. Yes. So that works as long as all of your forces lie along one axis.
Oh. Okay.
But if you've ever got something like this, where some of your forces are vertical and some of them are horizontal,
Yeah.
that falls apart a little bit. Follow? And I'll be honest, what you just did is how I taught my honors students, and then like halfway through the chapter, we did a problem like this, and it didn't work. And it was like, oh, oops. So, I learned by experience.
Yeah.
All right, good, you guys? All right, so we need to do more of this. We'll finish this up either Thursday or Friday. Tomorrow, you guys have time to work. We're looking to test either Tuesday or Wednesday next week. You guys have a preference? Wednesday. Do people have stuff on Tuesday, or is it just we need more time to work? Well, one person at a time. What?
BC Calc has a test with Monday or Tuesday.
Okay, BC Calc Monday or Tuesday test. What else? Any objections to Tuesday, to Wednesday? Okay, so let's tentatively plan Wednesday with the caveat that if we finish stuff early, we might have to start chapter 13 on Tuesday. Okay? Yes.
Okay, so 0.5 right at point Q. Even though, like, what's stopping it from going down this way?
The fulcrum.
What isn't the pivot point? Oh, so that's still there. I thought you moved this over to point Q.
Oh, I gotcha. Oh, no, yeah, so, no, the forces all still stay where they are.
Okay.
The idea is there's nothing magic about this point that means that it has to rotate about that point. I mean, it sort of like intuitively makes the most sense.
Yeah.
But, yeah, so leave the fulcrum where it is. And what I'm saying is, So the net torque, the torque from this would be 588 times 0,
Okay.
right?
Yeah.
The torque from this would be 1764 times 1.5. That's making it rotate this way.
Yeah.
And then these two forces are making it rotate this way.
Right, I just
So
thought you-
ideally, this torque will cancel those torques.
I thought you moved this over, and that's
I
why I was
gotcha.
like, that's
Hey guys, real quick. Well, never mind. I'll see you Thursday. Have a good day.
Bella, bitte.